All right, hi folks. So here is today's video lesson. We're going to start polynomial inequalities. We're going to start the way that we normally do with a warm-up. And I'm going to give you 4 minutes to do this warm-up. And go ahead and pause the video, try it on your own. When you're done, you can unpause it and I will go through it. But really give it 4 minutes worth of effort. Don't not do it. Do it. All right, cool. Go ahead and pause the video. All right, and I am assuming that now you are back having completed these problems, or at least hopefully 1 or 2 of the 3. Let's go ahead and go through how we would solve some of these inequalities. All right, so I recommend doing this graphically. I think there are ways to do it without, drawing out graphs, but this is the one that I'm going to recommend for you. As I say for, all the problems that we do, multiple methods are available or possible as long as you are accurate, as long as you are reliable, make sure that you can show your work. So there's, evidence of your thought process. But for notes, I'm going to just do this graphically. So let f of x equal 1/2 x plus 4. So let's call that a y-intercept of 4. I know that there's going to be a positive slope of 1/2. And what I'm looking for is the interval, right? Interval of x values over which f of x would be less than or equal to 0. So that would mean that our function f of x has to be below the x-axis, right? Really anything over here to the left. Right, so again, in terms of x coordinates, I can think that our minimum x value for this interval would be -infinity. We'll use parentheses for that. But then we have to figure out our maximum x value for this section of the graph, and that would be at this x-intercept here. Right, so the question would be, okay, what's the x-intercept of this function? You could just do this with slope and work backwards from your y-intercept, or if you want to do it more algebraically, we should be able to get the same answer. But let's say that y is equal to 0. Well, I mean, let's not say it is. It is. Y is equal to 0 at an x-intercept. Right. So my drawing wasn't quite to scale. It happens. We're going to find that this x-intercept is at -8. So that'll be the x value for our interval, right, where we are going to end the interval, because at this point, beyond this point, f of x will no longer be less than or equal to 0, right? F of x being the y values, right? We're looking for our y values that are less than or equal to 0, and that would be over here. Right, so the question then is, do we want parentheses or bracket? Right, in this case, we're going to want a bracket because our inequality says that f of x should be less than or equal to 0. At this x-intercept, right, we just said that y was equal to 0. So at this point, we are satisfying this condition of the inequality, which means that the point where x is equal to -8 is good for our inequality, and we can include it in our solution set. All right, so final answer, -infinity to -8 inclusive. Right, I'm going to do that again for the medium. I'm going to build up a little bit of speed here. I didn't give you axes this time, but I'm hoping that you sort of extrapolated and knew that you would need axes. Let g of x equal -2x plus 4 squared. This is telling me that the vertex will be at -4, 0, right? And this could be in factored form or vertex form, depending on how you want to look at it. But -4, 0. And negative a values, this parabola will open down. I don't really particularly care about all the other points because this inequality is just relative to 0. All I care about is whether points are above or below the x-axis, right? That's all that's important for this inequality. So solve the inequality g of x less than or equal to 0. Again, state your answer in interval notation. So where is the function less than 0, where do we have negative y values? Right, that would be everything to the left and everything to the right, right? All those y values are negative. Right, but think for a moment, why then would I not want to state a solution set of negative infinity to infinity? Right, think for a moment, why would that not be the interval that we are looking for? Right, the answer is very similar to why we used brackets up here, right? We used brackets because y was equal to 0 at this point, right? Y is also equal to 0 at this x-intercept, but that's not good for our inequality, right? We do not want points where y is equal to 0. We just want points where y is strictly less than 0, right? So this interval is including the x value of -4. It's not going to work for our inequality, right? In this polynomial, when x is equal to -4, y is equal to 0. So we will have to exclude that 4 from our interval. Say 4, -4. Exclude the -4 from our interval, right? So negative infinity up to -4, right? We'll stop at -4, and then after -4, continue on to infinity. The whole right half of this parabola is good for our inequality, right? And as we talked about before, if you want to write this as all real numbers but not -4, I'm totally good with that. Just make sure you get your notation correct. All right, and I'll do the last one even quicker. Let me throw down some axes. Come on, man. There we go. I've got a root at 0 with a bounce, where x is equal to -2. I'll have an intercept that looks like a cross. And then when x is equal to 10, we will have a bounce. I'm seeing an odd degree with a degree of 5 and a positive lead coefficient. That's telling me that I will have these tails, and then cross, cross, bounce, bounce. So where is h of x greater than or equal to 0? It would be here and there, and also here. Right, those are all the sections where the curve is above the x-axis, where all the y values are greater than or equal to 0. And I'm going to write an interval here that I see a lot, actually. I should have a bracket here. And then we'll talk about why it's really not a great answer to the question. All right, so this is an interval that I will see a lot for a question like this, which really isn't a great answer, for the reason being that if I was sort of to vocalize what this interval is trying to communicate, this interval is telling you start at -2 and then go up to 0, include it, but stop, but then also start at 0 and include that and go up to 10, but stop, but then also start at 10 and keep, right? Like all of this is redundant. There's no reason to have a break here if I'm including 0 in this interval and also in this interval, right? Same for 10. I don't need to stop at 10 if I'm just going to keep going right after, right? This really isn't a great way to write your interval. It would be better to just start with the value that you actually want to start with, right? And I want to start at -2. I don't want any values that are less than -2. But don't put an n value on your interval until you hit an actual stopping point, right? If h of x is greater than or equal to 0, I don't want to stop at 0 because this is a good point. Everything to the left and everything to the right was also good for the inequality. Same for 10. I'm going to keep on going, right? The best way to write this interval would be like so. Right, -2 inclusive to infinity. So zoom out so you get a better look at this. Right, but 3 types of inequalities, scaling up in intensity, linear, quadratic, polynomial, right? And this is sort of like the baseline of what we need for today's notes. All right, let's advance to page 2. The goal today is to get through pages 2 and 3, and then we can double back for the rest tomorrow. All right, let's take a look at this. Let f of x equal -x cubed plus 2x squared plus 3x. Determine the interval over which f of x is negative. All right, so definitely will want a set of axes so I can get some graphing going on like we did with the previous problems. But you'll also notice that this function is in standard form, not super conducive to graphing. We like to graph out of factored form, but I think that would just mean that we need to get it to factored form, right? So let's see what we can do with this function. I see a GCF of x. I'd like to factor that out. And I'm not super, happy when I have to factor with the negative a value. So let's take the negative with it. That'll leave behind an positive x squared minus 2x minus 3. Right, so factoring a negative x out of all of those terms. And as I say, you don't need the area model if you can get this done without it. Looks good to me. All right, but of course, if you are factoring things incorrectly, I am going to ask you, where's the area model? Where's that at? Right, so don't write it if you don't need it, but if you do need it, put it down. So we've got 3 roots here for our cubic function at -1, 0, and 3. So -1, 0, and 3. We had a negative lead coefficient, odd degree. So knowing my tails, I'll throw this down. And then these were all crosses. So I can cross through those intercepts like so. Right, so at this point, just a graphing problem, which we've done before. But now determine the interval over which f of x is negative. Right, and here's the thing that you do have to remember. Write it down if you need to. Put it in your notes, put a big star, highlight, whatever on it. 0 is neither positive nor negative. Right, 0 is neither positive nor negative. And I'm going to add this. It really isn't relevant to what we're doing, but for some reason, kids never seem to know this. But 0 is even. It is an even number. 0 is even. The same way 10 is even. The same way 20 is even. The same way -30 is even. 0 is even. For some reason, I say that, and then kids, at least like 1 or 2 per class period, will be like, I don't think that's true. And then we have to go into a whole discussion about why 0 is even. Anyway, let's not do that here. I want to know where f of x is negative, right, where it has negative y values. And the fact that 0 is neither positive nor negative means I don't want to include the points where y would be equal to 0, right, because that y value would not be negative. So for our solution set, looks like I want to have a -1 exclusive to 0 exclusive, union 3 exclusive to infinity. All right, so just tying together some more skills that we've done before to elevate to this type of problem. I would be very curious to know if you can do the next 2 problems on your own. I highly encourage you to pause the video at this point, try this on your own, or with group members. I don't know, like obviously I'm out of the classroom, do what you think is best, but try it without me guiding you through it for 2 and 3. And when you're ready to pick up the video, you can unpause and I will go through those solutions. All right, and I'm assuming that now we're back after you've unpaused the video. Let's go ahead and try out these problems. Solve the inequality x to the 4th minus 2x squared less than 15. Common mistake that people will do here is they'll start factoring right away and they'll be like, okay, x squared and x squared minus 2, and that's less than 15, right? And so then they have to graph, and then they're going to have, a bounce at 0, and then they'll have, root 2 and negative root 2. And how could I possibly know, right, what's happening relative to 15, right, or y is equal to 15? You can get it done this way. It's very hard to do it this way. I'll just be honest about that. All right, I think if we're going to work smarter, not harder, let's just rearrange some terms. Right, so if we subtract 15 from both sides, right, and the previous inequality was true, then this resulting inequality must also be true. X to the fourth minus 2x squared minus 15 is less than 0, right? And this will make it very nice and easy because then we're just comparing things relative to the x-axis. Right? All we got to do is just figure out how to graph this polynomial, which we've done before because this is just a factoring problem of a quartic in the quadratic style. So, and if you've done the area model for this, awesome, terrific, love that for you. I'm looking at this and I'm saying -5, +3. Yeah, that feels right. All right. So if I want to find the roots of that polynomial, right, then I can apply zero product property. It's technically a separate process. I'm going to delineate it as such because this is an inequality and these are equations. I'm just going to break those off and treat them as separate. All right. So in terms of roots for x, I got plus or minus I root 3 and plus or minus root 5. Now here's the thing. I root 3, I mean, being imaginary, I feel pretty obvious that we're not going to be able to plot this, right? Can't plot an imaginary number on a continuum of real numbers, right? There's no spot for this on the x-axis. So these are the only two roots that are going to give us actual x-intercepts on the graph, right? So when I go over to graph this function, right, I'll have an intercept at -√5 and at +√5. And that's pretty much it in terms of x-intercepts. Right. So when I look back at this polynomial, I see an even degree and a positive lead coefficient. That's telling me that we will have tails like so. There will have to be across each of these of multiplicities of 1. There's probably more curvature happening in here, more detail, but that's beyond our pay grade right now, given that comes from complex or imaginary roots. So I think this is good enough because, again, all we want to know is whether our y values are above or below 0, right? In this case specifically, whether they're below 0. So the part of the graph that has y values that are less than 0 would be right in here. And since we said that this inequality has the same solution set as this inequality, I think we can answer the prompt by saying -√5 exclusive to +√5. And again, I'm going to remind you, your estimation is only when you need to figure out where in space along an axis to put an x-intercept. If you have to provide roots of a function or an interval or anything else where you're not actually drawing something with proportions, give an exact answer, right? The estimation is just so that you can proportion your graph correctly. Right, -√5 to +√5. Let's go for problem 3. This is going to be another problem where we need to factor before we can graph. I am seeing 4 terms and not any, weren't provided any zeros. So this is not going to be a polynomial division problem. To me, this looks like a factor by grouping. All right, so I'm just going to go with the method that I saw the most on the test. I told you that you could do area model or just a pretty straightforward algebraic style. I saw more people attempt the algebraic style, so that's what I would go with here. You're, again, welcome to do area model. I think that's great. Should end up with the same answer, right? Should not be different, you and I. 3x, I should take out the GCF first. You hate to see it. You hate to see it. Okay, well, we'll live. I think we'll be fine. That feels right. So then between these two terms, right, x minus 2 can be factored out. And factoring out that parenthetical, leaving behind an x cubed minus 9x. And then I'm seeing that GCF in the latter term, which I should have factored out at the beginning. But you know what? So it makes this so nice is that I can do these, in different orders. All right, so x minus 2, 3x, and x squared minus 3. All right, if we apply a zero product property to find the roots, all right, 2, 0, and plus or minus root 3. So drawing in some axes here, put a root at 0. We've got a root at 2, and then for the radicals, I just need to know whether they are going to be greater than or less than 2. But root 3 is less than root 4, so root 3 should be less than 2. All right. Again, an even degree and a positively coefficient would give these tails. All of our roots had a multiplicity of 1, so there is no bounce. It's all going to be crosses. So cross, 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 cross. Then we're looking for intervals where h of x is greater than or equal to 0. And so here we have our positive y values, and I will include those intercepts because y would be equal to 0 at those points. So negative infinity to negative root 3 inclusive union, inclusive 0 to root 3 inclusive union, 2 inclusive to infinity. All right, so there's 2 and 3. That really is the process for solving these polynomial inequalities. Try to see if you can just get a graphical representation of the function, and from there you're just looking at where the positive y values are versus the negative y values, figure out which of those are relevant for your inequality, and then just use the graph to figure out your solution set. Again, make sure that you write it in interval notation, right? And just as a reminder, you have to know, if you're going to write an interval notation, you have to know when to use brackets versus parentheses. And some people are still doing this, but you need to make sure that you're putting the lesser value on the left and the greater value on the right, right? We are increasing least to greatest as we move left to right in our intervals, right? Don't be crossing up and putting values in the wrong order when you write in interval notation. All right, let's move on to page 3. Now we're going to go backwards, right? We're going to write a polynomial inequality given a certain solution set. All right, so I'm going to look here. The fact that we are using parentheses, right, on our values, or anything that's not infinity, that's telling me that there is not going to be an equal to, right? So in the previous problems, when we had less than or equal to, greater than or equal to, we would use those brackets to include our roots, right? The fact that those aren't here, it's telling me that we're not going to do anything with the equal tos, right? Strictly less than or strictly greater than. And because it's less than or greater than, you actually do have some freedom in how you answer this. There are multiple answers that are possible. Right, but the first thing I'm going to do is throw down the roots of the function. Right, I can tell that they're going to be the roots because these are where our intervals are cutting off, right? 4, 6, and 7. Also, I'm actually going to duplicate this now so I can use this later for another solution. But let's just focus on the blue for now. Right, so the interval of negative infinity to 4, the interval from 6 to 7, need to have y values of the same sign, right? It wouldn't make any sense if I said that I want positive y values here and negative y values there, Because really, what inequality would you be writing where that would be the case, right? Doesn't really work out that way. So let's say that we want positive y values here and there, right? We also then need to make sure that we are not using that same sign for any points that are not a part of our interval, right? It really wouldn't make sense for this interval from 4 to 6 to also have positive y values, because then 4 to 6 should be a part of our solution set, right? It isn't, so this can't be positive, right? Our y values need to be negative here and there as well. Right, and if that's the case, then let's just draw in a graph that matches the signs that we want our y values to have, right? I've drawn a graph in like so. Right, and once we have that, we just kind of have to write a polynomial that would match our roots and our end behavior. So I'm seeing an x minus 4, an x minus 6, and an x minus 7, right? End behavior looks good because this would be cubic. It would have a degree of 3. So odd degree, opposite tails, looks good. But we will need a negative lead coefficient. So this would currently have a positive lead coefficient. Let's introduce a negative a value so that overall we have that negative lead coefficient. Right? This polynomial in factored form, I think, pretty well represents the curve that we have. We are not done because we do need to write an inequality, and we haven't done that yet. So if this is what we're after, right, and we said that the positive sections are for our solutions, right, the fact that I don't want any equal to's in here, the last part that we need is just to say that this polynomial is going to be greater than 0, right, strictly greater than 0. Right, but as I said, you definitely have freedom in how you answer this. You could have, -2, -3, -5/19, right? Whatever a value you want, as long as it is in fact negative to give you that negative lead coefficient overall. Or if you don't want things to be negative, you can just, write a different inequality altogether, right? So I'm going to highlight the sections that I want. And I will say it is a strategy that some people use just to not mess around with a values and just always guarantee that your a value, or rather your leading coefficient, is going to be positive, right? If we set this furthest right-hand section to be positive, right, then we will always have an upwards tail on the right, and that's always going to come with a positive lead coefficient. So you don't have to mess around with a values, right, if you always set this right-hand section to be positive. Now, I'm not saying that you have to do that, but it is a strategy that people use, right, just to keep things simple and eliminate some other parts that you would have to account for. Right, so we'll do that. We'll set this section that is not in our solution set to be positive with its y values. That would mean that this section would have to be positive. These y values would have to be negative and negative. Right, and then we can continue the graph like so. And so similar to above, x minus 4, x minus 6, and x minus 7 would be our factors. And the whole point was that we don't have to mess around with a values now. So I'll just double check. It is a positive lead coefficient, and this end behavior matches that. So that's good. The actual part of our solution set would be for this section of the graph, where the y values are less than 0. And again, we don't want to set this equal to 0 because our interval was exclusive at these x-intercepts. All right, so two possible solutions for you here. You do not need both of them in an assessment scenario. Like if this is a test question, it just says write a polynomial inequality. That's singular. You don't need both, you just need one. All right, so I'm going to let you try B, C, and D again without me guiding you through it. So go ahead and pause the video and try it on your own. Don't not do that. Do it. All right, and I will see you in a few minutes. All right, and again, I'm assuming that you are unpausing the video, having tried some of these problems yourself. I can go through this, and we can go a little bit quicker. Let's go, let's do it. Throw it on an axis. I've got roots at -5 and 0 and 8. It's going outwards towards -infinity. These are the sections for our solution set. And if you want to try that strategy of just always setting your right-hand section to be positive, you can do that here. So I want negative, positive, negative. And so this looks like x plus 5, or root of -5, times x minus 8. These sections that we've highlighted before have y values that are less than 0, right? But notice that we used brackets, so we want to include these x-intercepts, meaning that this should be an inequality that is less than or equal to 0. Right, and just based on that, if you pick the other direction for your graph, I would expect your answer to be negative x plus 5 times x minus 8 greater than or equal to 0. Right, with other answers being possible if you just commute these factors and move them around. Right, let's check out this over here. We've actually seen this notation before. This is what we call a singleton. So I'm hoping that you recognize that. Or if not, I'll just redefine a singleton for you. A singleton is a set that only has one value, right? That only has one value. So the relevant x-intercepts here are -2, 3, and 5. You can very easily see that the sections that we want for this are going to be -infinity to -2, 5 to infinity. But the singleton says that we want to include just this point in our inequality. Right, so let's set our furthest right-hand section to have positive y values. We'll do the same thing here, right? I've got negative y values there and there. I'm going to draw on a graph, and you tell me what's not so great about it. I mean, don't literally tell me, like I can't hear you, but think for a moment, right? What's wrong with what you see here? Right, and hopefully you're responding. I mean, like thinking, like again, don't talk. Like I can't hear you. But we're missing this x-intercept, right? We're supposed to include this point in our inequality. We should have a graph that's passing through this x-intercept. Very clearly, that's not happening, right? So hopefully you're picking up on what needs to happen here, right? We just need a bounce at x equals 3. Right, and I think this covers everything that we want. We want a graph that passes through our x-intercept, that has negative y values directly around it. We've talked about before about how that creates a bounce, right? Positive y values here and there. I think we're in a good spot. Right, and so even just beyond the brackets, I think that might sort of give you an indication as to why we want our inequality to be greater than or equal to 0, right? Or if you chose a different direction, less than or equal to 0, right? But the or equal to being the important part, because at this exact point, y is equal to 0, right? That's what creates the singleton, right? The bounce is the only point in this stretch of the graph where y is equal to 0. Oh my goodness, I forgot the square. So there's a bounce. We were just talking about how there's a bounce. You hate to see it. You hate to see it. Okay. Now I think we're good. All right, let's get to our last one here. This one is actually kind of the inverse of the previous problem. And maybe you saw that if you've done the problem already, or if not, we'll see it in a moment. All right, -5, 0, 9, and 15. Relevant sections for our inequality are being highlighted here. Right, but notice that we do not want to include 0, right? So what I wouldn't do is make just two positive sections, right? Instead, each of these will be treated individually. Let's make it very clear that we don't want to include 0 in our solution set. Right, what this all is sort of hinting at with our parentheses would be that, you know, we want an inequality that is not equal, or rather doesn't include the equal to 0. It's just strictly less than or strictly greater than. And the way that we can exclude this 0 is just by making the y values equal to 0, right? The fact that we're excluding this is telling you there's a bounce, right? Positive y values around this x-intercept, but the actual y values when x is equal to 0 should not be, in this case, greater than 0. Can't really be less than 0 because that would create another x-intercept that we don't have in this representation, right? But if we make a bounce, it's going to work out great for us. So let's write up polynomial. I've got an x plus 5, an x, and I will incorporate the bounce this time. I'll put a square in there. X minus 9 and x minus 15. That seems right. That feels right. All right. We put our positive section over here, so I don't have to mess around with that negative a value or the negative lead coefficient. Should be taken care of for us. And then I want these positive sections, right? Again, I don't want the or equal to, because we're seeing all these exclusive values. So just greater than 0. I think we are good here. All right, so that wraps up the video notes for today. Hopefully that was good for you. I think I gave you homework tonight, so you can go ahead and work on those IPs either by yourself, with people. I don't really know how much time there's left in class for you at this point, but hope that's good. We'll see you tomorrow and we'll pick it up there. Bye.